Hello everyone, how's it going? I hope you're all fine today. We are going to talk about some examples regarding chapter 3 and finding a strength of concrete sections, ultimate flexural strength. And we are also going to look at different sections, see how we can come up with the equations for finding the strength. And in one example, we will also look at designing one beam from scratch. The beam that we are going to design will be very similar to what we are going to have in the project. In future assignments, we will design the beams that we have already found the loading on, and then we will see based on the loading how we can design the sections and find the reinforcement and specify all the details for that beams. So in the next few sessions, I will talk about these topics and we will solve examples. Each example will take one session based on my experience in in-person and actual class sessions, because we usually have some talks and discussions with the students and there are usually some questions about the procedure. And of course, writing it on the board takes time. So I'm going to give you some time at the end of the class to repeat solving the example at home, because I know solving it as I present it and describe it would not be easy. But I will leave some time at the end of the class for you to repeat solving it again at home, and then I'm available after the class for WebEx meeting and we can definitely discuss the questions. If you have any question, we can definitely discuss it over there. Just send me an email and we can definitely switch to WebEx and discuss the issue or your question over there. In previous discussions that we had during the presentation, we talked about finding the ultimate strength of beams, and we said we have certain assumptions in finding the design, in finding the flexural strength, and one important assumption was about the reinforcement in the tensile region. We said this reinforcement or the steel that we have in the tensile region has yielded. Based on that assumption, we could find the tension force over here, and then by having the tension force, we could move forward and find the equilibrium in the section, and then once we have the equilibrium, we can simply find the strength of the section. In the first example that I prepared over here, I'm going to show you a situation in which the steel in the section has not yielded. So the assumption that so far we could simply use in the examples that I solved during the presentation file will not be useful over here, and I'm going to show you how we should find the strength of the section and also how we should find the phi factor that we have over here for finding phi mn or flexural strength of the section. So over here you can see properties of the section are given. Dimensions, we have 2 feet. Height of the section, 1 foot or 12 inches. The width of the section, we have a rectangular cross section and we have 2 rows of number 10 bars. And as you can see, the spacings are given 2.5 inch from centroid of the first layer to the very bottom of the section, and then 2.5 inch the distance from second layer to first layer. The question is asking about finding flexural strength, reduced flexural strength, or phi mn for this section. So let's begin the solution by the assumption that we had in all concrete sections when flexural loading and flexural strength is considered. We have to always begin the solution by having this important assumption. As you can see, the assumption is about the steel and the fact that the reinforcement that we have over here should be yielded. What is the basis of this assumption? This assumption is based on the recommendation that I showed you in the code. Let me move to the code and show you the part that we had. So as you can see over here, this is the part that we have from the code. And as you can see, it says for non-pre-stressed beam with axial load less than a certain amount. In our case, all the beams are non-pre-stressed. The section should be tension controlled, right? And the reason for that is ductility and having enough deformations when the section has reached the yield point, and from yield point to failure point, we want to have ductility. We want to have a behavior like this. If the section is tension controlled, we can see such a thing. If section is not tension controlled, we will see a behavior like this. Instead of having this much ductility, the beam fails over here. So based on this assumption, we have always this procedure in the solution. At first, we assume reinforcement in the section in the tensile region has yielded. So that is the basis for this equation over here. I have to calculate the tension force based on area of steel multiplied by the yield strength. Area of steel is based on number 10 bars. We have 6 number 10 bars. If you look at the table that we had in the first presentation, when we talked about the steel, we said there is a table in different textbooks or in different references that summarizes all the bar numbers, diameter of each bar, and area of each bar. For number 10 bars, area of number 10 is equal to 1.27, and based on this, I can simply calculate the tension force as 457,000 pounds, or about 460 kips, 460 kips, the tension force over here. So we are familiar with the strain and stress distribution. A strain distribution is always linear regardless of the stage that we are looking at. As you remember from the second presentation or chapter, I said based on the very basic flexural theory that we have in reinforced concrete sections, a strain distribution is always linear. That's why we have this situation. Over here you can see this line is the neutral axis, and then based on the stage we can define a stress distribution. If the section that we have or the section that we are analyzing has cracked, we have one form of stress distribution. If it is not cracked, we have another form of stress distribution. And then the third stage was ultimate strength, which is the situation that we have over here. We are looking at the ultimate stage. That's why a stress distribution looks like this. Actual compressive stress distribution, we said, has a nonlinear distribution, something like this. But since calculation for this parabolic, semi-parabolic shape is difficult, we simplified it with this rectangular shape. So we replaced this nonlinear semi-parabolic shape with this rectangular shape, and to do this we had certain considerations. The intensity of the stress is 0.85 F prime C in this rectangular shape, and depth of this rectangular compressive stress is A, and that's what we need to find based on equilibrium. So tension force, we calculated it over here based on the assumption of yielding steel over here. Then we have the compressive region. The compressive stress is distributed over here. Total compression force that I have is a stress multiplied by area that we have under this stress, that is A, depth of it multiplied by B, width of it, which is width of the section. As you remember, if I want to look at the 3D view, it looks like this, and then this is applied over here in the compressive region. This is A, and this is B. And this region is the region where compressive stress is applied. Depth of it is A, width of it is B. The amount of stress is 0.85 F prime C. That's why when we want to calculate compressive force, we have this equation. So, compressive force that we have over here is equal to 0.85 F prime C multiplied by width of the section B and then multiplied by A. F prime C is given as 3,500 psi. That is written over here. B is 12 inches, that is width of the section. And then A is the parameter that I don't know. So as you can see, by multiplying these together, we have this term as the compressive force. So the section is in equilibrium, tension is equal to the compression, and based on that I can find A, or depth of compressive block, as 12.8 inches. So far, very straightforward, and everything that I did so far is the procedure that we are going to have in all concrete sections. The next step is to check the assumption that we had over here. We said steel has yielded, and based on that we calculated the tension force. Now I need to check that assumption. How can I check that? We said we have to look at the strain distribution. I have to calculate this C, or depth of neutral axis, and based on the similar triangles that we have over here and over here, I can write the ratios for this side over this side equal to this side over this side. These are similar triangles. Based on the ratios that we have between the sides of these similar triangles, I can find the strain over here. Why am I doing this? That is all because of this slide, or this part of the code. As you can see, when we want to see the amount of strain in the tensile region, I have to look at the strain at the bottommost layer of the steel. See epsilon T that we have over here. All right, now I should be able to move this. All right. So as you can see in the section over here, we have the reinforcement, and epsilon T, the tensile strain that we need to use for finding the class of section, whether it is tension control, compression control, or the other situations, is defined based on the bottommost layer of steel. So when I want to calculate the strain in the tensile region, I have to look at the bottommost layer of steel. So let's return to the example that we had. And now I have to look at the strain over here. And by finding the amount of strain over here, I will be able to see if the reinforcement that we have has yielded or not. Right? So we could find A, depth of compression block over here, 12.8 inches. We know that A is equal to beta 1 multiplied by C. That is the relationship between C and A, and that is coming from, again, this part of the code. As you can see, this is the part that gives us the information about beta 1, and this is the equation in the code. By the way, I posted the 14 version of the code, ACI 318.14, because library so far does not have access to the very last 2019 version of the code. These slides that you can see, these are screenshots of the very last version, 2019 version, because I thought that is the version that we need to learn, because once we start working in companies and in consultant companies, we need to use the last version of the code. But the thing is that these parts are pretty much the same in all versions. The critical parts of the code that has changed from 14 to 19, I will specify them, and I will clearly tell you that this part is brand new in 2019, and you have to have in mind that this is something that we need to always use and look for 2019 version. There are two major differences. One of them is about shear design. I will talk about that in future. And the other part is about finding effective moment of inertia when we are looking at serviceability and deflection calculation. Except those two, everything else is pretty much the same, and you can simply look at the files that I posted as the 2014 version or ACI 318.14, and you can use that for checking what we have in the code. So we wanted to find C, depth of compression block, and this is the equation that we need to use. A is equal to beta 1 by C, and beta 1 is calculated based on this table. If F prime C is from 2,500 to 4,000, it's always 0.85. If it is greater than 8,000, it is always 0.65. And if F prime C is between 4,000 to 8,000, we have to use this equation, 0.85 minus 0.05 multiplied by F prime C minus 4,000 divided by 1,000. This is the table and the way that I need to use beta 1. In the example that we are looking at right now, F prime C is 3,500. It is smaller than 4,000. So beta 1 is 0.85. Let's return to the example. And we talked about this strain distribution. And based on this, I can find this strain. That is why I need to calculate C. So this is the equation. C will be A divided by beta 1. We said beta 1 is equal to 0.85. And then A, we found it already as 12.8 inches. So dividing that by beta 1 will give me C as 15.06 inches. That is C. I can simply look at the strain distribution. And then write the ratios based on this side, and this side, and this side, right? So epsilon t over this side, which is dt minus c. As you can see, this distance is equal to dt. I'm calling this dt because this is the distance from top to the very bottom layer of reinforcement. The typical d that we always use in calculations is distance from top to the centroid of a steel. But right now, when I want to calculate the strain, and then based on this, understand the class of section, I need to look at dt and the very bottom layer of steel. So this is dt, and then I can say epsilon t over this distance, which is dt minus c, is equal to 0.003 over c. This is this important ratio, and this is based on these triangles. And then I believe everything should be pretty much clear. The only thing that I don't know over here is epsilon t, right? C is already calculated. dt is based on the geometry that we have in the section. We can simply put that in the calculations that we have, or in the equation. If I go back, look at the geometry of the section, total height is 24 inches. 24 minus 2.5 is equal to 21.5, right? So that is the dt that I have in the equation. So based on this equation, I can find epsilon t, and once I do that, epsilon t is equal to 0.0013, right? So this is the strain over here. Now to see if the steel has yielded or not, I have to compare it versus yield strain. If it is greater than the yield strain, steel has yielded. If not, steel has not yielded. So let's compare it with the yield strain. What is the value of yield strain? That is based on this very famous and basic equation that we have about stress and strain. The stress divided by Young modulus is equal to a strain, or basically a strain by Young modulus gives us a stress. The stress that we are talking about is Fy, yield strength of reinforcement that we are using in this section, and Young modulus is Young modulus of steel, which is always 2.9 multiplied by 10 to the power 7. So this is how I can find the yield strain. As you can see, it is calculated over here. Fy is 60,000, E is 2.910 to the power 7. For all types of steel, that is the Young modulus. As you can see, this is the yield strain. So comparing the strain that we have over here at the bottom layer of steel, or epsilon t, versus yield strain, you can see steel has not yielded, which has two meanings. First, section is not tension controlled. This section is compression controlled. As you remember, we had these classes of section. We said if this strain is equal to the yield strain when concrete reaches maximum compressive strain, the section is balanced. When this strain is smaller than yield strain, when concrete reaches maximum compressive strain, section is compression controlled. And then when this strain is greater than the yield strain, then we have two situations: transition zone and tension control. So over here we have this situation, or the compression control section. The other thing that we have to understand in this situation is that this force that we calculated over here is no longer valid, because we said tension force is equal to area of steel multiplied by Fy. And now that we check the strain over here, we can clearly see that the strain is smaller than the yield strain. So it means that the reinforcement has not yielded, and that's why this is not valid. I have to put the actual stress of steel over here, and it is smaller than yield stress, or Fy. How should I do that? I have to modify my tension force based on the actual strain that I have over here. We know that the strain is always equal to a stress divided by Young modulus. So now that I calculated the strain over here, I know what is the strain. I can simply multiply it by Young modulus and find the stress, right? And then once I find the stress, I can multiply it by area and find the force. That will be the actual tension force that we have over here, right? So let's follow this procedure and see how we can analyze this compression control section. T, or tension force, should be updated. That is the major difference that we have in the analysis. Whenever section is compression control. So now I need to calculate the actual strain that we have in the reinforcement and then find the tension force based on multiplying the stress by area and then use this tension force for finding the strength of the section. So right now I could find this epsilon 1, right? That is the epsilon t that I calculated over here, and this is the value of that. Now I need to calculate the strain at the level of second layer, and that is what I have over here. So epsilon t is calculated. Epsilon 2 can be calculated in a similar way. I have two similar triangles, one up there, the other one, this one, and based on this I can find the value of epsilon 2. Right, epsilon 2 over this side, which is d2, the distance from first layer to the top, minus c, that is this distance, epsilon 2 minus over d2 minus c, this distance is equal to 0.003 over c, right? Based on this, I can find epsilon 2, the strain that I have at the first layer of steel. Now that I have the strain, I can simply find the stress, and that is a strain multiplied by Young modulus. So I'm going to multiply these strain values by Young modulus, that will be the stress, and then I'm going to multiply them by area to find the tension force that I have at each layer of steel. That is done over here, and as you can see, once you do that, you can find the tension forces. It is, I believe, pretty much clear. I tried to make everything very clear to follow, and as you can see, these are the tension forces. And now that I have the tension forces, I can calculate the strength of the section, right? There is one thing that you can also ask about, and you may already think about it, and that is the depth of neutral axis, C, or A, because we found C based on A. As you remember, at first I assumed the steel has yielded, right? That was the first step. Then based on equilibrium of that tension force and compression, I found A. Based on A, I found C, and based on C, I'm calculating all the strains. But the thing is that all of these values are coming from this assumption that the steel has yielded. We found that the steel has not yielded, which means all of these A and C values are not really the actual value. That's why if I want to accurately calculate all of these parameters, I mean A, C, and then the strain values, I have to continue this analysis. See, I found T1, T2, instead of saying T is equal to AS multiplied by Fy, now I calculated these based on the strain values. Now that I have the total tension force by adding these two together, I have to update my equation of equilibrium. See, now I can say T is equal to C, summation of these two is equal to 0.85 F prime C BA, and find the new value of A. See, the A that I already calculated was based on the assumption that the steel has yielded. Now this A is based on the fact that the steel has not yielded and the actual strain is calculated. As you can see, I can continue this in several other calculations. I can find A, now I can find the real value of C, then I can find these new strain values, then again I can find tension forces, then new equilibrium, then again A, again C. We have to continue this until we reach convergence, which means we have to continue this until there is a small difference between old value of tension force and new value of tension force. I just continued it in one kind of calculations, or in one trial attempt. So this procedure is called trial solution, which means we have to have several tries in order to reach convergence. And you can just compare the tension force that I have right now and in the earlier try. The first assumption was about 460 kips. Now it is 230 kips. See the difference? You can continue this solution at home until you reach convergence. That is a good thing to do because it helps you understand the behavior. But I'm not going to give you such an example in the exam, and to be honest, if you look at different textbooks and references, you will not find such an analysis or such a situation where section is compression controlled. Most of the time, if people see a situation like this, they will quickly say, okay, this section is not following the code rules and it is not valid. We cannot do anything with it. That is right, but I just wanted to show you what is the procedure when section is compression controlled. This way, I believe you can have better feelings about analysis of concrete sections and what we're really doing when we are analyzing sections. Again, you will not see such a situation in exam problems because, as you know, it is taking time. Even right now, I just stopped after one try, or actually two tries, and then I'm going to just use A value and also tension force to find the strength of the section. But as I mentioned over here, I have to, if I want to be very accurate and find the very actual strength of the section, I have to update C, and by updating C, I have to update these strain values. Once these strain values is updated, I have to update the tension forces and then compare these tension forces with these that I have from the previous try and see if the difference is high or they are converging. If the difference is high, I'm talking about 1% difference. That is the kind of convergence rate that we usually have in a structural analysis. If the difference is high, we have to continue this analysis until we reach convergence. Anyway, we could find the new values for tension forces, and I'm going to stop here. These are the values that I'm going to calculate and use in my strength calculation, and that is this equation over here. As you know, when we were looking at this famous situation, when we had all the reinforcement yielded, we could simply put the tension force at the centroid of the reinforcement like this, and then find the moment because of tension about compression, and that would be Mn, right? The same idea can be used in this situation. The only thing is that I have to find the moment because of two things. One, this force, the other one, this force, and all of those moments should be calculated about compression force. The idea is the same. I just have to consider two forces because of the situation that we have in this example. The first moment is T1 multiplied by D1 minus A over 2. I'm basically considering this distance between T1 and C. As you can see, that is D1. This distance is D1 minus A over 2 will give me the distance from the forces, right? So D1 minus A over 2. A is the last A that I calculated, and then the other term is for T2, and then the distance that we have from compression to this force, that is D2, this distance minus A over 2, half of the depth that we have as A, or depth of compression. So that is calculated over here. That is, if I calculate all of these, as you can see, the term is always in units of pound and inch because force is in pounds, dimensions or distances are in inch. So the moment is in pound and inch. It is not comment. I divide it by 12,000 to change it to keep food, and that is 330. I could find the nominal strength so far. Now I have to include phi factor. What is the phi, or what is the strength reduction factor? We need to look at the code and find the slide that we had about a strength calculation, a strength reduction factor, or phi. That is over here. As you can see, based on this string that we have to look at this diagram or this table. They are both the same. The only thing is that for this line, we have the equation, as you can see over here. This equation is basically the equation for this line. But anyway, I have to look at the class of the section. Is it compression controlled or transition or tension controlled? And based on that, find the correct phi factor. This is the diagram that we need to use, this orange kind of line. That dashed line is used for columns. We will talk about that later. But this solid line is the thing that we need to use. We are looking at a compression controlled section, which means this region. And that is why in this region, phi is equal to 0.65, right? That is based on this graph. If you want to use the table, this is the column that we need to use. So all of these are the things that we need to see, because this is for a spiral situation, and that is the equation for this dashed line. That is for columns. These are the values that we need to use for beams. We are looking at a situation where the strain, or epsilon t, is smaller than the yield strain, or section is compression controlled, and phi is equal to 0.65. All right. So based on this, I can go back, look at the beam that we had, and in this beam, phi is equal to 0.65. I have to simply multiply this by the strength, and that is why phi mn will be 216 cube foot. As I talked to you earlier, and as I described, we stopped the solution at this stage. I didn't update the new C value, or I didn't update the C, this C based on the new A. You know, if I wanted to continue this, I have to say C will be equal to A divided by beta 1. Based on that, I have to update C. Once I do that, I can update the values of epsilon 1 and epsilon 2, and then continue the procedure. You can do that at home, but based on these values, we could find the reduced strength of a compression controlled section. I'm going to leave the rest of the time for you to repeat this example at home. Make sure you understand the procedure and you know how to exactly calculate each of these parameters. And then if you have any question, I'm available. Just send me an email. We can switch to WebEx and then discuss the question. Thank you.